Hi guys, so we are going to do a little bit more math with our genetics today. And so we're going to talk about probability and look at the probability of certain genetic traits and do some calculations with that. So what we're doing today is called binomial expansion. Your assignment is on the back of that chi-squared worksheet that we did yesterday. So this is usually a little bit harder for students, so I'm going to give you until Tuesday to get this done. So that gives you kind of an extra day on Monday if you have some questions to ask. If you've taken statistics, you may have done something like this before. But let's go ahead and get started. So when we do the law of probability, we have two different rules that we like to use. So the addition rule and the multiplication rule. So let's start down here at the bottom with the addition rule. So the addition rule looks at the probability of any one of two or more events will occur, okay? And so in the addition rule, we add the probabilities. So if you have two or more events that could occur, you're looking that at least one of them will happen, okay? So for example, let's say a couple's going to have a baby and they are wanting to know if it's going to be a boy or girl, like a boy or a girl collectively, not a boy, a 50% chance boy or 50% chance. They want to know that their child will be a boy or a girl, And so you have to look at the probability of having a boy, which would be 1/2, and the probability of having a girl, which would be 1/2. And when you add those together, you get 1, which is equivalent to 100%. So when they have a baby, it's going to be a boy or a girl, right? It's going to be one or the other because really there's no other option. But we are looking at it's going to be one of two things one of those options. And so we add those probabilities together. The multiplication rule is a little bit different, because we are looking at independent events and that they're going to happen in a specific combination. And so we multiply the probability. So let's say, for example, the couple's going to have a baby and they want to know if it's going to be a boy. So that would be 1/2, right? That's going to have a hitchhiker's thumb. And so if you do the Punnett square, whatever, maybe you find out that, they have a 1/4 chance of having a hitchhiker's thumb. And so when you multiply that together, you get 1/8. So having a boy, a child that is both a boy and has a hitchhiker's thumb is 1/8, okay? So a little bit of difference there in whether you multiply, if you're looking at two things together, or adding when you're wanting any of those combinations, okay? And so that's the multiplication and the addition rule for probability. So we are going to use this tool, and it is a tool for being able to determine probability, and it's called Pascal's triangle. And so Pascal's triangle is a mathematics tool. If you've taken statistics before with Miss Brooke Gregory, then you have probably used this. And so you see up here in the top left how this tool is generated. And so you've always got ones down both sides, right? And then the other numbers are derived by adding what's above them. So 1 + 1 makes 2, 2 + 1 makes 3, 3 + 3 makes 6, 6 + 4 makes 10. And so you can generate your own Pascal's triangle pretty quickly, okay? So I'm going to step away from this right now, and we're going to look at a practice question, and I'm going to show you how you'll use Pascal's triangle to be able to work through the problem, okay? So this is binomial expansion again, and this is our first practice problem. So phenylketonuria, or PKU, is an inherited disease caused by a recessive allele. So that means to have PKU, you must be little p, and that would give you PKU, okay? If a woman and her husband, who are both carriers, now I'm not sure that we have touched on this term, but a carrier is the same thing as a heterozygote. So it means they carry that allele for PKU, but they don't express it because they also have the dominant allele. And so a carrier is like this, right? So both the woman and her husband are carriers. So if they have 3 children, what is the probability that each of the following? So let's take a look at this first one first, okay? Our question is asking us about 3 children. So when we go back to our Pascal's triangle, we're going to use this row that has 3 on the outside. If we'd asked about 7 children, we would have used this row, okay? So I'm going to use these Pascal's triangle, and these numbers here, 1, 3, 3, 1, are going to serve as coefficients to generate a little equation, okay? So I'm going to write out the equation, and I start with 1, and it goes a to the 0, b to the 3, plus 3, a to the 1, b to the 2, plus 3, a to the 2, b to the 1, plus 1, a to the 3, b to the 0. So what you see here is that I started with a to the 0 and I stepped up. So I went a to the 0, a to the 1, a to the 2, a to the 3. I started with b to the 3 and I stepped down. So b to the 3, b to the 2, b to the 1, b to the 0. And I use those coefficients, 1, 3, 3, 1, from my Pascal's triangle, okay? So that's how you would do it every single time, okay? If we were doing one in this row and you were generating that expression, you would do 1, a to the 0, b to the 6, plus 6, a to the 1. We're going to step it up, and we're going to step b down, okay? Plus 15. We're going to step a up to the 2 and step b down to the 4. Plus 20, and they're both going to be equal, a to the 3, b to the 3, and so on and so forth. Hopefully you get the idea there. And so when you look at these exponents, they always add up to the number that's on the outside. 0 plus 6 equals 6. 5 plus 1 equals 6. 2 plus 4 equals 6. And the same is true for ours up here that we did. Okay? So let's go back to our problem. So what is the probability that all 3 children are of normal phenotype? Okay? Well, what these A's and B's represent, and you can call them whichever way you want them, it doesn't matter, but we will say A represents a normal phenotype and B represents PKU, okay? So our question says we are looking for the probability that all 3 children have a normal phenotype, okay? So we want 3 A's and 0 B's, 3 normals and 0 PKU. So that's this part of the equation right here. 1 a to the 3rd, b to the 0, okay? I'm going to write that down here. 1 a to the 3rd, b to the 0. Now, what I have to do is I have to plug my probability of having PKU or of being normal in for A and B. And so I get that from my Punnett square. If we do the Punnett square, big P, little p, big P, little p, and we fill it out, you should see that 75% of them are normal, okay? 25% has PKU. So normal was 75%, PKU was 25%. Oops. So I'm going to plug in 0.75 to the 3rd and 0.25 to the 0. Okay? And so I can put this in my calculator, and I get 0.42 probability, which is equivalent to 42%. So there is a 42% chance that they will have 3 children that are normal, okay? Now, some of you that may be pretty mathy are probably going to say, Miss Brown, that was really a lot of work. We could have just done the Punnett square, found 0.75 or found 75%, and then multiplied 0.75 times 0.75 times 0.75 and also got 42%. And for this question, you are absolutely right. You could have done that, okay? Some problems that I'm going to give you on your assignment and some genetics probability problems, you don't have to use Pascal's triangle for and this method, okay? But some of them you do have to use, all right? So let's look at the next one. One or more of the 3 children have the disease, okay? So we are looking for 1 or more kids with the disease. And so that means we want our B to be 1 or bigger. So that's going to be all of these. All of those have a B of 1 or bigger. So in order to solve that, you have to do all of those things and add them together, okay? So I'm running out of room a little bit here, but I'm going to do my best. 1, A was 0.75 to the 0, B was 0.25 to the 3rd, plus 3 times 0.75 to the 1st, 0.25 to the 2nd, plus 3 times 0.75 to the 2nd times 0.25 to the 1st, okay? And we're going to add those up. So let me work on that here on my calculator. You can be working it as well. And so what I got was 0.5717. And so that means when we convert it to a percent, 50%, 57.17% chance that 1 or more of the 3 children will have the disease. 57% chance that 1 or more of the 3 children will have the disease. Okay? The next one, all 3 children have the disease. Okay? So this is actually one of those cases where we could just look at, we're looking for children with the disease, which we had said was 25%. And so we can do 1/4 times 1/4 times 1/4, or 0.25 times 0.25 times 0.25, if you wish to do it that way. And that turns out to 1 out of 64, which is 1.6%. Okay, that they would have 3 children with the disease. Alternately, you could also do that with the binomial expansion. All 3 children have the disease would be this part, okay? And notice what you're going to do there is you're going to raise 1/4 or 25% to the 3rd power, which is essentially the same thing as multiplying it 3 times. Then you're going to multiply it times a to the 0. Anything to the 0 power is 1, so it's going to make it the same answer. And then again times 1, which is still going to make it the same answer. Okay? Now let's look at the last one. At least one child is phenotypically normal. Okay? So we want at least one that's normal. So we want our A to be 1 or bigger. So that's going to be all of these. Okay, all of those. Now, I don't really have room to write this all out, so I'm going to have to kind of write on top of stuff. 3 times 0.75 to the first times 0.25 to the second. 3 times 0.75 squared times 0.25 to the 1. And 1 times 0.75 cubed times 0.25 to the 0. And I'm going to add those up. I'm doing this on my phone, so it's taking me a second longer. So this equals 0.14. This is going to equal 0.42. And this is going to equal, is that right, 0.42? Yeah, okay. So when we add those up, 0.42 plus 0.42 plus 0.14, then we get 0.98, or 98% chance. So if they have 3 kids, 98% chance that at least one kid is going to be phenotypically normal. Okay? All right, let's take a look at one more practice problem. If you feel like you got this really well, then you can turn me off here and go ahead and do the work. But if you need a little bit more practice with it, then stay tuned. Okay? Now, on this one, I didn't give you what the parents are. So let's say the parents are both heterozygous, okay? So congenital analgesia, the inability to feel intense pain, I wish I had that, is controlled by a single gene where the recessive allele p causes congenital analgesia. So that means p is going to be CA, okay? Anything with a big P, sometimes we'll write it like that, big P, and then anything that comes after it, meaning another big P or a little p, would be normal. Okay, so what is the probability that their first child will not be afflicted with CA? So we want to do our Punnett square of the parents to see our probabilities. And this may be one that, you don't really have to do. You kind of know what it is. So 25% chance that they're going to have CA. So the question says, what is the probability that the first child will not have it? So we're just looking here independently at one child. And so we can get that answer by looking at the Punnett square. And we would say 75% chance that their child will not have that. Okay? The next one, what is the probability that their child will be a boy and afflicted with CA? So to be a boy, we would say that that's 1/2. And to be afflicted with CA, we said a while ago that was 25%, so 1/4. Okay, so 1/2 times 1/4 is 1/8. If you put that in a percent, it's going to be 12.5%. I don't care if you put it in a percent or a fraction, doesn't matter to me. What is the probability, in the next question, that all of their first 4 children will have CA? Okay, so this one we could do full binomial expansion for, or you could just probably more easily just multiply it out. So if they have first 4 children, the probability for that they will have CA for the first child is 1/4, for the second child is 1/4, the third child is 1/4, and the fourth child is 1/4. And so we add that up. It's 1 out of 256, or 0.39%. So not very likely that they're going to have all of their kids with CA, all 4 of their kids with CA. Okay? And we multiplied them because we're looking at 4 different ones that they would all have it. So we're looking at that collectively. And the last question, if the couple has 4 children, what's the probability that at least one of them will be afflicted with CA? So this is a case where we're going to have to use our binomial expansion, okay? So let's slide over here, maybe. Let's slide over here to our binomial expansion, and we're going to use this row because it has the 4 on the outside. So when we write out our expression, it's 1a to the 4, b to the 0, plus 4a to the 3, b to the 1, plus 6a to the 2, b to the 2, plus 4a to the 1, b to the 3, plus 1a to the 0, b to the 4. Just stepping those up and down. Okay? Now we are looking for at least one child that is phenotypically normal. So let's say we're going to call A normal and B to have PKU. Or not PKU, CA is what we're dealing with now. At least one child, okay? So we want our A, our normal, to be at least 1 or bigger. So that's going to be all of these, okay? So we'll plug those probabilities in and solve. So our probability of normal was 3/4 or 0.75. And then our probability of CA was 1/4 or 0.25. So 0.25 to the 4th times, 0.75, sorry. Make sure to get those numbers in the right spot. To the 0. And I sure hope that I have not transposed or done anything crazy with these numbers. Usually when we do them in class, I have y'all kind of checking me along the way. But here, I don't have that. So I hope I've got it all right. All right. So I'm going to plug these into my calculator. So 0.75 is 0.316. Okay. The next one is 0.105. Okay, sorry, I did this one wrong. That should be 0.421. Okay, so when we add all of these back together, I get 0.316 plus 0.421 plus 0.21 plus 0.0468, and I get 0.9938. So 99.38% chance that one of them will have CA. If they have 4 children, what's the probability that at least one of them will have CA? 99.38% chance. Okay? So if you have any questions on this, let me know. Go ahead and get started on your practice problems, and if you run into trouble, then feel free to holler at me. Y'all have a great day and a great weekend.